He is a senior architect at NVIDIA, focusing on applied research in networking for scalable systems and HPC. Previously, he was a postdoctoral research associate with MIT, where he focused on benefiting from the rise in silicon photonics technology to scale performance beyond single chip limitations. He received his PhD from UC San Diego. And today his work is called Rosebud, making FPGA-accelerated Middlebox development more pleasant. Rosebud is a reference to the Citizen Kane, which is considered widely the best movie ever made. So if you guys didn't see it, you should probably. So with that, Moein, take it away.
Thank you for the introduction. I'm Moein. I'm going to present Rosebud, a framework for FPGA-based Middleboxes. I started this work about 5 years ago at UCSD. It finished while I was at MIT, and I'm going to present 5 years of my life in 12 minutes. So network Middleboxes are flexible in network compute. Think of it, whatever our switches or our routers don't do, we want a Middlebox to do that for us. For example, we can have some attacks and we want to prevent those. So we do intrusion detection system where we check for some specific signatures in the packet payload and then process the headers to know, for example, what is the context. One point is these Middleboxes are running on backbone internet, and which means that we are operating at liners of 100 to 400 G or even more than that. This requires a tremendous amount of compute power. We use CPU-based Middleboxes, but they cannot keep up, so we require to split the traffic among several cores on several servers, which is not efficient. Obviously, we can benefit from hardware acceleration, especially FPGAs sound like an ideal case. They are reprogrammable, so you can change them if the application or the rules change, and then they can hit the main part, for example, the base filter, and just send the remaining to the CPU to be processed. Because of that, actually, we are seeing some FPGAs which are tailored for this type of acceleration, that they have some hard IPs specifically for that, or we have higher density FPGAs with newer technology nodes, or multiple dies to be able to keep up with that rate because of the required parallelization. We even have partial reconfiguration that on the fly, without stopping the system, we can change part of the hardware. As an example, there was a paper in OSCI, Pegasus intrusion detection system, which used this idea of hybrid CPU and FPGA, and they could achieve 100 gigabit per second on a single server. And what they do is they compile the rules into some accelerator and then program the FPGA with that. That being said, that FPGA is really good. At the end of the day, whoever did some FPGA development knows it's a pain. And when we are operating at such line rates, it just exacerbates the situation. We really need some deep knowledge of the FPGA features. The new capabilities that they added, to use them efficiently, we have to have a good knowledge how to use them. The fact that our clock rates are slow, it means I need more parallelization to keep up. It means I need more resources. Then the placement and routing becomes more complicated. So I have to provide some hints to the tools. And then we have a lot of heterogeneous accelerators, and the packets have different size. So the timing is rather unpredictable, which makes the orchestration of them very intricate. And then if you change one of the accelerators, it might break the logic of the orchestration. So we have to redo it, which makes it worse. And on top of that, we have to debug hardware that is processing millions of packets per second. It's not just some ALU testing A plus B. And the point is, the debugging is just Byzantine, because we have very limited runtime debuggability at most, some logic analyzer that we have to figure out how to trigger. And then the development cycles, like we have to spend hours just for simulation or for a placement and route to finish. So at the end of the day, most of the time of a hardware developer for Middleboxes is looking at this, some waveform from the simulation and trying to find a bug, even if it's there. I was like, come on. In Middlebox, when there was software, things were so nice. I had Docker, Kubernetes, breakpoints. What do I have here? Nothing. Like some milliseconds of waveform that I might find the problem, and debugging, I have nothing. And there could be bugs even in my debugger that I'm trying to debug the system. So we present Rosebud FPGA Middlebox framework. It brings the simplicity and comfort of software development to FPGA Middleboxes. It achieves 200G throughput. It doubles the PICOS's performance. It reduces dev time from weeks to months to just days. And for what? It only has a negligible latency and area overhead. How do we do this? The main piece is a new abstraction, reconfigurable packet processing unit, or an RPU. The idea is to sprinkle a little bit of software next to our hardware accelerators to do the management, and then we use some shared memory to receive the packets. All of that within a partially reconfigurable block so we can update it on the fly. The main idea is to keep the abstractions that Middlebox developers are used to, the software ones. So these network-targeted FPGA features, they can be abstracted away as packets. The packets arrive in my memory, and I use some DMA descriptors to say what I want to receive or how to send it out. Similarly, I can communicate with the host using some descriptors. Regarding the orchestration, let's do the orchestration among hardware accelerators just like there are some functions. I feed them the data as their input, I call them, and then I receive the data when they are ready. And then if you want to change the function, you can update it with partial reconfiguration. And the debugging, I mean, it's software, both on the RISC-V or the host. So it becomes much easier to trigger or catch the buggy scenarios, kind of like a breakpoint. And then you don't even have to spend any dev cycles to fix the orchestration logic bugs because you are doing it in software. All of this sounds good, but is it actually feasible at 200G? The insight is reversed Amdahl's law. So what does Amdahl's law say? That if you have, for example, something takes 5% of the time, and you improve it even by 20x, at most you are getting improved by 5%. Reverse, if the orchestration is taking less than 1% of the processing per packet, even if I make it 5 times worse, it's just 5% overhead. So we can do the orchestration using a slow software core sitting next to our accelerators. You might say, well, let's say I'm using the RISC-V cores at 250 megahertz. They are still very big, and it can kill the acceleration benefits. That's where Rosebud comes into play. We make some architecture designs to make this orchestration more efficient. For example, for the data movement, we make an optimized DMA engine in RPU interconnect, which connects each of these RPUs to the rest of the system. Whenever a packet comes, it copies the packet into the shared memory and gives the descriptor to the core. Similarly, for debugging, if we want to get a memory dump, we can talk with host to the RPU interconnect, or interrupts, debug, you name it. Another optimization is if hardware wants to wait for software for any data movement, it'll take a long time, but we can use FIFOs as just job queues. That software has to just fill the queue, and the hardware can just pick some item so they can run asynchronously. And finally, memory system plays a critical role. Let me go a little bit deeper on that. We had to make a new memory subsystem architecture for RPUs. On the left-hand side, you see the RISC-V with its data memory and instruction memory. The point is, if I want to put the packets in its data memory, then the access time takes a couple cycles, which would be very slow. But I want to only parse the packet header. So the packet headers are copied into the local memory of RISC-V, which can be accessed within a single cycle, so I don't have to spend time there. And the packets themselves, they go to a high latency memory, which has a couple cycles due to pipelining, but my accelerators can access it in a pipeline manner, no problem. And obviously, accelerators themselves have some local memory. The nice thing is, over that shared memory, for example, for the packets, the RISC-V can also access them or update the packets if necessary, or use it as a scratchpad. And then hosts can have access to all of this memory to load or do debugging. You might say, okay, these are cool. It gets better, but still, 200G? But as I said to you, we are, for middle boxes, for CPU-based ones, we could distribute the traffic among several of them. So let's just do that within an FPGA among several RPUs. So let's say I have 16 RPUs. It means each of them has to only keep up with 12.5. It is much more doable. We optimize the rest of the logic distribution, host access, Ethernet ports, all of that for you, and place them statically. Then we have course parallelism through this workload-based load balancing that we mentioned, which makes it easier for each of them, and you need less parallelization. And finally, we lay out PR regions. We need some expertise, so the user doesn't need to know those. And another beauty is right now only the load balancer and the RPUs are within PR regions that you have to care about placement and routing. The rest is already fixed. Let me show you what that means on an FPGA. We did an implementation on a popular Xilinx FPGA. Here I'm showing a layout with 16 RPUs. So the only thing that user has to do is put their logic in the RPUs, put whatever policy they want for the load balancing into the load balancer, and the placement and routing is just this. The rest of the system, which is a lot, we already take care for you. The Ethernet MAC, how to talk to hosts, how to have virtual MAC, how to have those RPU interconnects, switching, messaging, debugging, all of those. You can read the paper for more details. And regarding the performance here, I'm showing the packet forwarding performance with 16 RPUs. We vary the packet size from 64 bytes to jumbo frames 9 kilobytes. On the left-hand side, I'm showing the bandwidth achievable. The dotted lines show the maximum possible 100G and 200G achievable rate. And as you see, if I use one port or two ports of the FPGA, for 128-byte packets, I can fully hit the line rate. Regarding the latency, I only see 0.7 to 7 microsecond of latency, which is very negligible. We are sitting on the edge of the internet. We have milliseconds of latency. As you see, even if I have low load or high load, I don't see that much a difference on the performance, and I see a nice curve up. So we wanted to understand where is this latency coming from. We actually estimated the serialization latency, which is the amount of time it takes for a packet to come to our RX buffer, then go to each of the core memories and the reverse direction. And actually, it's almost all of the latency. That's why we don't see a change between the two. One more thing that you might see is about 64, why it jumps up. The point is, as we see on the left-hand side, we cannot fully keep up with the rate. So when I cannot, my RX buffer gets full, and I have to pay the latency. There is no free lunch. But the main point of this slide is multiple RPUs help to amortize software and the delivery overheads. I'm going to wrap up with two case studies. First, a basic firewall that we demonstrate how simple it is to build an FPGA Middlebox with Rosebud. We wanted to drop some packets based on some IP block list. So we made an accelerated to match IPs. Literally, it's a case estimate in Verilog. We could have used HLS as well. And this is the code that is running on there. So I just look at the source IP based on the pointer where it sits in the header. I send it to my accelerator through some memory mapped I/O. I read the result. If I want to drop it, I just set the length to 0. If I want to forward it, I swap the port between 0 and 1. And then I say just packet send. We already provide a C library for you to be able to send those. And all of this took less than a week. And we could do 200G for packet sizes, 256 bytes and more. Finally, the Pegasus IDS that I talked from the OSDI, we ported it to Rosebud in only 3 weeks. And the performance from 100G, we went to 200G. Because of more efficient memory system, we were able to put more of their logic and get more parallelization. And another beauty is that now we can update the rules during runtime. With their system, you had to program it once. And another thing that I think it provides you is rapid prototyping. In their application, they have to implement everything. But for example, here we're like, what if we do the reassembly and stuff in hardware, in software? It'll be less performance, sure, but I can do rapid prototyping. So for 1024-byte packets, that is the typical packet size on internet, if I do it with hardware, I can do 200G, which is awesome. But actually, if I do the reassembly in software, I still can do 100G. So I can test my system and build it one step at a time. Just for comparison, we also run the same thing on a Snoeren CPU, and then without any acceleration outside the CPU. And as you see, the performance is less, and it's less efficient. So with Rosebud, we could achieve 200G with software running on Wimpy cores. Felt really nice. And Rosebud is fully open source, and you can use it to make your 200G Middlebox today. You can check it at GitHub. Thank you.